Hello, this is Professor Kuehn. Welcome back to my lectures on space, time, and motion, where we are looking at Chapter 11 in a student's guide to the great physics texts. This chapter is titled From Conic Sections to Projectile Motion. In my previous lecture, we looked through the very beginning sections of this text. This is beginning on page 141. And in that section, we talked specifically about the idea that's presented in Theorem 1, Proposition 1. So I'll just read this. A projectile which is carried by a uniform horizontal motion compounded with a naturally accelerated vertical motion describes a path which is a semi-parabola. This is the main point that Galileo is here making. And in the next section, what he does is he reminds us of the properties of a parabola. After all, he's going to say that a projectile follows semi-parabolic motion. So what do we mean by a semi-parabola? Well, what do we mean by a parabola? And so he's reminding us on page 143, figure 11.1, of how one constructs a parabola. You might recall there that if we draw a cone and we cut it with a plane parallel to one of the edges of the cone, then we get a parabola. That's what we went through in our last lecture. Now in this lecture, I'd like to jump ahead to figure 11.3. And this is the example where Galileo explains why it is that an object which falls off of a cliff after rolling across the surface of the cliff undergoes parabolic motion. So here, line segment AB represents the top of the cliff. Line BOGLN represents the face of the cliff. And you might imagine a ball rolling along from line A to B. If there's no friction, which is a dubious assumption, but let's assume that's the case. If there's no friction, then it will be undergoing uniform horizontal motion. When it gets to point B, then it will begin to fall off the cliff. But, and this is the critical point, he argues that the horizontal motion is still a uniform motion. So it's still going to be moving horizontally at a constant velocity or a constant speed. But then on top of that, it acquires a uniform acceleration in the vertical direction. And as a result, it goes along the curve BIFH. And he argues specifically that this is a parabola or a semi-parabola, a half of a parabola. How does he know that? Well, what I'd like to do is walk through a proof of this, but I'm not going to do it quite the same way that Galileo does because I'm going to use a bit more modern notation, and I hope that's all right with you. So the question that we're asking here is, how do we know that projectiles, or a projectile, move in a parabola, as he was claiming in Theorem 1 on the previous page? So how do we know that? It's clear, and he says this earlier, that they move in a curved motion, but saying it moves in a parabola is a specific kind of curve with a particular mathematical form. And he reminded us of what the parabolic form was. That is, if you think the vertical direction is the y direction, and the horizontal direction is the x direction, so we might set up a coordinate system where this is y and this is x, so y is going downward and x is going horizontally, then if it moves in a parabola, that means that y should be proportional to x squared. That's what we mean by a parabola. Okay, so he has to somehow demonstrate that the y-coordinate is proportional to the square of the x-coordinate. How does he do that? Well, let's do it in a few steps. So first of all, he says that this is undergoing uniform horizontal motion. Remember back in chapter 8 of the text, we defined what we mean by horizontal motion, and this means that if it's undergoing uniform horizontal motion, the x distance that it travels, that is the horizontal distance that it travels, is equal to the horizontal speed, that is how fast it's moving horizontally, multiplied by the time elapsed. This formula works if something is undergoing uniform horizontal motion. Or in other words, if we wanted to write this in terms of variables, x equals the horizontal velocity times the time. Okay, so that would be the distance it moves along the x-axis. So this is going to be our first equation in the succinct form. Okay, what's point 2? Well, uniformly accelerated vertical motion. We talked about that back in chapter 8 as well. And this implies that in the y direction, that the distance it moves in the y direction is proportional to the square of the time, right? And in particular, we derive the relations that y equals 1/2 the acceleration in the y direction multiplied by the square of the time. Or if we wanted to write this succinctly, we would write y equals 1/2 at squared. So that is the distance that it falls as a function of time. So this is the horizontal distance it moves. Horizontal distance. And this is the vertical distance. Notice what we're doing here is that we are somehow breaking this problem up into two separate and independent motions. That's a critical recognition here, is that the horizontal motion maintains the same type of motion, that is horizontal uniform motion, and the vertical motion is uniformly accelerated vertical motion. And the fact that it's moving horizontally doesn't change the fact that it's uniformly accelerated vertically, and the fact that it's uniformly accelerated vertically doesn't change the uniform horizontal motion. Now notice that these are both parametric equations. That is, the value of x, the distance it moves in the x direction, depends on the parameter time. As time increases, the x position changes. So x is a function of time. And also y, that's a parametric equation. Y is a function of time. So in modern parlance, we would call these parametric equations because both y and x depend on the parameter time. And now the nice thing about parametric equations, which you might remember, is that we can eliminate the variable t and write y in terms of x. So in particular, x of t was equal to vh times t, and y of t was equal to 1/2 at squared. Well, what we can do is we can solve this first equation for the time. We can write time equals x over the horizontal velocity, and then we can take this and we can plug it in right there for the time, and when we do that, we get y is equal to 1/2 a times x over vh squared. Where do we go from here? Well, we can simplify this and say y is equal to 1/2 the acceleration over the horizontal velocity times x squared. Notice here that if the acceleration is constant, which we're assuming that it is, that's uniform vertical acceleration, and if the horizontal velocity is constant, which again we're assuming that to be the case, the horizontal speed doesn't change, then this whole thing in front is a constant. In other words, the y location is proportional to the square of the x location. Does that ring a bell? It should, because y is proportional to x squared implies that this is a parabolic motion. In other words, that it moves in the form of a parabola. And that is the main point that Galileo is making in figure 11.3.